welcome to this webinar. We're talking about the Libra project that it's calling the Facebook cryptocurrency. And all the information that we are sharing is the open source that the Libra project shares in their hub. If in the hub of the developers. So let's see what is Libra. And in the Libra page we have the front page, and I'm gonna start thinking what is Libra. So let's move to see more about this.
Remember when these were fast? And these? Technology has improved the world around us. So why is it simple to send one of these anywhere in an instant, but not money? What if we made money truly global, stable, and secure? What if everyone was invited to the global economy with access to the same financial opportunities? Introducing Libra, a new global currency designed for the digital world, backed by the belief that money should be fast for Ope in Lagos, simple for Saul's family business in Manila, and secure for Betsabé when sending money home to Mexico City. It's powered by blockchain, making it safe and accessible, no matter who you are or where you're from. So join us as we move towards a world where money works for everyone. This is Libra, and it's just the beginning.
So let's move to under the hood to understand the concept about the BFT protocol that is calling Libra BFT protocol, that in the page that they share with us, they calling a variant of the Hopstock protocol. So let's move to the GitHub, official GitHub, to understand all the things about this project. So we are here in the official GitHub of the Libra, and we have find here all the specification about the protocol. And these specifications are interesting for so many ways. So you want to know about this protocol specification, you need to check this GitHub repo and understand all the concept that this protocol specification has. So far in this source code you can find all the folders and the implementations that the blockchain Libra are doing right now. It's in real time. So you can see here that 2 hours ago was a commit, so it's so new in that kind of way to see. So let's move to see more things about this specification, this protocol specification, and understand all the concept of the BFT protocol. So let's move to see all the protocols that we have. So in some meaning, we can understand that the Hopstock protocol includes 2 basic protocols, that it's calling the basic Hopstock protocol and chain Hopstock protocol. For simplicity, we only review the basic Hopstock BFT protocol, that in some way is similar to PBFT, and determine BFT. There are n equals to 3t plus 1 participants. So you can find that P0 to Pn less 1 and at most t of them malicious. The view is defined and changed in the same way as in the PBFT. And what is the PFT? It's the practical Byzantine fault tolerance. That it's a paper written a long time ago, and it's incredible paper that have the basics to make the practical the Byzantine fault tolerance. So the major difference between PBFT and Hofstad BFT are that the PBFT participants broadcast single messages to all the participants. So of two participants send the single message to the leader participant in a point-to-point channel. That means that the PFT use a mesh topology communication network, so Hofstad uses a star topology communication network. So the communication network is different in the PFT and in the Hofstad. So let's see, for example, the PFT. You can find out there this protocol so easily, and you can find in the internet. You can Google it like this: practical Byzantine fault tolerance. That are the meaning of PBFT for P of practical, B of Byzantine, F of fault, and T of tolerance. And it's interesting way to see how this protocol specification works. So let's move to see the first thing about this PBFT protocol to understand the meaning of the concept about the kind of topology network have this protocol specification. So we can find here the first thing about the normal case operation, and we can see that this state of this protocol make different kind of phases that are equal to the case of the Hofstad DST. So you can understand in this fig how is this runtime in the replica state. So you can find here how this different number that can be different nodes start the request, and the replicas start in different phases to finally get the reply in the origin of the request. So it's the first normal case operation. So you can find here the first fig of PBFT. So it's the similar between the PBFT and the Hofstad BFT. So far you can find how was the evolution of the BFT protocol in the sense of the topology of the network. So let's see a little bit a timeline about this kind of concept out there. So let's move to see this way. So let's log in. So we can find here a timeline about the evolution of BFT protocols to understand the glossary and terminology about to study this kind of BFT protocols that are so important and that matters. So let's move to see this little bit timeline to understand the concepts. So you are out there, you can ask me anything about this kind of protocol and specifications. So let's move to see And we can find here a little bit timeline about the evolution of BFT protocols. So we can find here in the date of this and publish it, the code and the paper message from bit message and step rounds. So it's the division of how this BFT protocol it's have different meaning for the setup that you can try it. So let's to see that in the 2019 we have the hot stuff, and this hot stuff was called a BFT consensus with linearity and responsiveness. And we saw in another different videos that the responsiveness it's a new concept to understand the meaning of the Byzantine fault tolerance in partial connect asynchronous network. But because we have in the Byzantine fault tolerance that is not so friendly change the variables of the protocol specification, or maybe find a good way to have this partial connect asynchronous network, because you are dealing with the complexity of the measures and the complexity to reach the consensus all the time, and with the Byzantine failures that you can expect in that kind of protocol. So you need to deal with this trade-off that the Byzantine fault tolerance protocol has in the mixes of the complexity of any kind of topology that you can find out there. Also, you need to see how the vector of the attack try to figure out how to make for example a denial of service that is called in the DOS attack, and you need to solve any kind of vector like hijack, maybe another kind of vector that involves a different way to see the BFT protocol. It's interesting to know all these kind of trade-off that the BFT protocol has. For example, this kind of challenging to design consensus protocol for distributed computer system in a asynchronous environment was for the non-malicious faults several practical protocols. This kind of protocols has been deployed in relatively closed environments. So that example was like, for example, in Google and Microsoft and IBM use a BFT protocol that is called Paxos in their storage or cluster management. So these kind of protocols are only relative closed environments. So in a blockchain meaning, you have another way to see how this environment is for the mazes. So in a blockchain, for example, you have two kind of approach, that is the permission net and the permissionless. So in the permission, you can decide who is going to join to the network, and in the permissionless, anyone have joined to the network. So this kind of two approach have a different environment. So it's a relative open environment. So it's a difference between this kind of partial connect asynchronous network, and you need to deal with the importance of propagating the decision measures of this protocol. So let's move to see more about the safety rules. And we speak in the glossary of the BFT protocol to understand different ways to see this protocol. And you can also check the other videos about Libra in the official channel and understand better this BFT protocol that's called Libra BFT. That's a variant of the hop-stop protocol that is divided in the basic hop-stop protocol and chain hop-stop protocol. And the big difference between the PBFT protocol and the hop-stop protocol is the topology of communication network. So another big difference between the PBFT, that is the practical Byzantine fault tolerance, is that the practical Byzantine fault tolerance uses standard digital signatures scheme. So hop-stop use threshold digital signatures scheme. So you can solve that the difference between this kind of protocol is the communication complexity of dealing the propagating decision measures for reach the consensus. So let's move to see more interesting ways, but in the code. So you can find the open source code out there, and you can see the Libra open source code. So you download it, and you can find here different folders of this open source, and you have here the folder of the consensus, and you can find different folders here, and the principal here is the safety rules folder, because you have all the protocol specification that the Libra BFT protocol have to understand the basics about of the basics of the importance of propagating decision measures. So far, you can also find this paper that is called the state machine replication in the Libra blockchain. And so far you can find the protocol specification in the technical way to build the Libra project and build the Libra blockchain. So you can find here all the protocol specification that have the Libra project. And you can find for all the definition that this state machine replication have. You can find in the open source code all the safety rules to reach the consensus about this kind of way to see the protocol. So let's move to see more code about this implementation, and you can find here a folder of the source code of this. And the important way of these safety rules are only say 6 conditions of this protocol. So you can find that the safety rules are how to in the importance of propagating decision measures, and the topology of the network communication, and the threshold of digital signatures scheme. So you have to deal with these kind of measures in the way to connect the protocol. So remember that in the hop-stop protocol, in the chain hop-stop, you have architecture different for any kind of BFT protocol that you can find out there. So for example, you can find here the chain hop-stop and the pipeline of this basic hop-stop. That is the way to divide this kind of complexity protocols to understand the connection of the protocol. So you can find here that have a same wave of the PBFT protocol. You have different phases, and how to this replica start to reach the consensus in the last way. But the complexity complexity of communication on network is different because you have a point-to-point communication. And you can see here that you have also phases, but you have the Keyron certificates, that it's an instance of the protocol specification, and you also have a different way to see these faces. But the standard schema is so equal in the way to understand the BFT protocol. For example, in the safety rules, you need to find that you have two concepts of this kind of protocol, that is the liveness. And what do you mean with the liveness in the protocol specification? So you can find that the liveness in the mean of the BFT protocol, you have a way to understand the protocol. You can also find here. So you can find here the liveness mechanism in the protocol. And you can see that the liveness delegates route synchronicity, and it means including the leader election and the decision when to enter a new round to a specific module called a pacemaker, that it's an instance in this kind of protocol. We now describe the pacemaker of Libra BFT in detail, as well as the policies of resharing records, cleaning the record store, and tracking commits to decide additional query all the operation. These machines are crucial for liveness, as we will see in the proof of section 8. So you can see that the meaning and the liveness mechanisms in the protocol, it delegates around synchronization, because in this kind of protocol you are dealing with the partial connect asynchronous network. So in the asynchronous network, you can find different theory about this kind of approach, and you can saw that for a synchronous network you have a Fisher, Lin, and Patterson that showing that there is another deterministic protocol for in the BFT problem in phase for a single failure. So this proof was in the search of different lemmas and theorems for how that this is not could solve in no deterministic protocol for BFT problem. So you need to figure out to understand how this protocol design to reach the partial connect asynchronous network. You need to find another kind of ways to reach the consensus in this kind of protocol design. And it's important protocol design, the partial connect asynchronous network in the Byzantine fault tolerance, because the principal bottleneck in this kind of protocol is the transaction per second. So if you have this partial connect asynchronous network, you figuring out how to escalate this kind of protocol. So you have also this non-deterministic protocol of the BFT problem that face for a single failure. So you have this kind of possibility that is called the possibility of Fisher, and you need to think in another assumptions for process this kind of data to reach the consensus in the way that you need for the protocol. So let's see more things about this liveness mechanism. That the important way to understand this is to figure out how to deal with the partial asynchronous network. So you can see here more successful runs in the Libra BFT, and you can find that it's so similar to the PBFT implementation. So let's move to the code and see more things about these safety rules. So let's to make a little bit zoom in. So let's start with the safety rules. So you have that the safety rules for the consensus are bot rules, commit rules, and ownership of the consensus private keys. So let's to see what is the voting rules in the protocol specification. So far, only can find this kind of protocol specification in the way of this paper, but maybe there is a private different way to see this protocol specification. Maybe in a GitHub repo that is private for only the members that are trying to build this BFT protocol, but it's only a speculation. But I think it's properly have this kind of protocol specification to make a better build. So let's move to see these button rules, and we can find that button rules is increasing the ROM and the processing of pacemaker updates. So you can find here that the button rules are connected with the processing of the pacemaker. So let's see more about this pacemaker. It's an interesting way to understand. You can also find the pacemaker in the page of the research that makes the technical perspective of this Facebook Libra BFT consensus. So let's see more about this protocol. Maybe like that. No, it's not working like that. Maybe you can find here like this. It's not working in that way. So maybe you can find that info about the pacemaker, the protocol specification of this, and the review of the pacemaker. So let's to see how this pacemaker works. You also can find this in the protocol specification to understand, because we saw that this pacemaker is connected to the button rules of the protocol specification. So let's move to the Libra GitHub. So we are in the Libra GitHub repo. Let's find this pacemaker under the hood. We have the test scope of this pacemaker, because provides a liveness. We have also that this is an event processor that needs that kind of way. That's currently way fusing. We have that the pacemaker have a time interval between the send and sync and plus static way. You also have the pacemaker. It's the way when a node enters a new round and it computes the leader and the maximal duration of that round using two predefinition function leader that contains this kind of input and duration that is the same input of the leader. Test function takes an input the round number n and the last test commit round node this kind of way to the node and the time they are invoking. A consensus node enters at round n where it receives a quorum certificate at round n less 1 or enough timeouts to form a different thing and the round n1 whichever comes first. The round n is the considered active until the node enters to a new round. When a node has active round, it may only vote for a block and round end authored by we also take the authorities by the leader of round n. So you can see that only you can have n equals to 3t plus 1 participants in this kind of protocol. So and almost t of them are malicious. So you need to figure out how this wave for a node enters a new round needs to have properly functions to take as an input the round number n and then let's commit round node n to the node and the time they are invoked. So you need to figure out how this works properly in the way to avoid the most t of them participants in the protocol. So let's move to see more about this pacemaker that it's all about how this neuron and starts and how this could be a manager of this neuron. Let's see more things about the pacemaker. So you have here that it's involved in all the process for propagating decision message, the protocol specification. So far you can see that the pacemaker is working in the time interval and have these conditions that have the way to make a new round reason and the pacemaker itself, and you have that is working in the way of modular way because the sequence of how this protocol start to manage the things that they need. So you can see here how this pacemaker is connected with the safety rules to make a better understand of how to deal with the partial connect asynchronous network that try the consensus to reach, and this is to have a better performance and a minimum delay in the service that provide this kind of protocol. So let's move to see more things about these safety rules. So we can find that the safety rules are responsibility for the safety of the consensus, and you have the three ways to understand this. That is the button rules, that is connected to the pacemaker for manage how this new node is connected and the ways to make a good decision of this message. And also we have the commit rules and ownership of the consensus private key. That is about the cryptographic primitives in the BFT consensus. So let's to figure out more about these safety rules. And we can find here interesting ways to understand this protocol specification. So let's to move this way, and let's start to making the implementation of the safety rules. So you have an implementation that will be a payload of the safety rules. So far, you need to put the data you want. So start to think in the function of these safety rules. So you have an author. The persistent storage. So you need to let the consensus key that's equal a persistent storage. You also have the consensus key. That's a safety rule of the ownership of the private keys. Expect something interesting way. This kind of protocol. Then let the validator signal aware of this validator will be sync until layer 1. Maybe it could be a no. You also need to understand how this self is a persistent storage, because you need to handle a lot of data, and start thinking in how to sync this validator and make something tricky way for the data that calling phantom data. That's a technical way to understand how this protocol works. So far you have this. That is the safety rules. So you have these three kinds, and you can show that you make a voting rule, how this could be a commit rule, and the ownership of the consensus private key. So let's see more protocol specification about these safety rules. So in this minute, the safety rules, you have different kind of approach, how to process, the main of this, how we work with the client side. Obviously the consensus state, that is the more important thing to deal the personal connect asynchronous network, and the trade of this implementation. But let's see more about the protocol specification. We can find the consensus state to understand more things about this consensus way. find here the consensus state. So let's do seed rules. Can find here the commit rule. And you can find here the stroke of the bolt. So you have here the epoch that works in ID epoch. So this epoch will be unique in some sense. It's a way to start the round. Then you have the certificate block hash and the state, that is the consensus state, then the execution state of the ancestor block if any double match, the commit rule of the vote, then the author you can find here that was about this safety rules of make new author and persistent storage. Maybe in the way of CDs, persistent storage. Get another safety rules that try to make the consensus key in a persistent storage. You also have the consensus key and expect something that is maybe unable to retrieve consensus. So it's a way to see this. So far you have here. So you can start to try the way to understand here. You also see how these block proposals propose the block with the things that they need to make a good connection. So the key insert certificate block. You can see that in the protocol specification you have certificate block shack. You also start in this protocol specification to understand how this block works. That's a command. So this is the network records about the Libra BFT and the protocol specification, how to reach this. So this threshold digital signatures scheme always is seeing the key certificate, seeing the hash of the key certificate. So you need to see this, and after of this you need to find all this thing to understand the way of how this key certificate works. So let's find more things about the key certificate in the way of the safety rules. So have here the current certificate, and you can also find here in the way of the architecture of the how this is connect in different phases, like the PBFT protocol implementation. So let's see more about this current certificate. You can find that this current certificate was maybe in this way better. Current cert is the way that you can find here. It's all about the highest current cert. And this current certificate have a sensor. So for fetch these results, you need to insert a key inserter. This is the way to fetch the results on how to reach the consensus. So it's the importance of providing decision measures for have a better performance to reach the consensus. So an interesting question about this is what happens if leader doesn't rely broadcast the sales measures in hub stuff. So it's interesting way to understand how it could be a different semantics where the client receives different responses. So it's the thing that the consensus of hub stuff is dealing. So you can find more things about the current certificate and also have the genesis of this. You can find here how this data is connected in the current cert with the certificate block and the ID. You can see here in the protocol specification and also in the block specification. So let's move to see more about this current cert. That it's in the safety rules. So you need to test this how this current cert is working. Very nice to Singer, the validate to Singer. And of course both the proposal for change this new view. So let's see more interesting way for this current cert. You have here key insert in how propose the block. So the key insert you need to make this proposed block and of course the bot proposal. Remember that the hub stuff is similar to PBFT and under my BFT. So you have the same thing about the proposals, votes, and on the way for the proof of stake meaning. It's a testing way if you want to build a protocol, a BFT Byzantine fault tolerance protocol from scratch. So you can figure out a lot of things about first. If you want to deal with the partial connect asynchronous, that's a thing that right now the consensus are dealing with the impossibility of Fisher that there is no deterministic protocol for the BFT problem in a phase of a single file. So that is the first statement, and also you can find the lemmas and theorems that prove that no deterministic way. So maybe you can find a MP harness solution. Maybe you can find different ways to see, maybe trying to randomize the input in PDF or a random meaning, and combine this kind of approach to have to deal this impossibility in the synchronous network in the partially, because one can be 100% asynchronous. You can see more about this key insert. It's about the highest key certificate to commit a block. So you can see here how it's all connect all this current certificate. So you need to understand how this is working in different phases that we saw in another video. So you can deep dive to understand more this thing. So let's move to see more things about the protocol specification. So see the queue. So we have data records. The core step, the Libra nodes consists on a collection of records. These kind of records are the blocks, the votes, Keyring certificate, which hold a queuing of votes for a given block and execution state, and optionally a commitment mix for Libra clients. So it's the way to make this in a permissioned way. So you don't have the queues, it's a way to make the permissionless state of the blockchain state. That means in some way the consensus state to reach the consensus. So it's an interesting way to how this queuing certificate works under the hood. You also have the data structures, that's the state, the command, the epoch, the run. You can find here what it's all about, what kind of data is. Of course, we saw the current certificate, they have the Porsche ID, the round, the certificate block hash. You also have the state, the commit the state, the votes, and the author. That's how this leader who proposed the certificate block should also send the key certificate. So you can figure out all of things here, but let's want to see more about these safety rules in the thing. Interesting way for handle this is the spinner process. So the spinner process, it's a way to see this binary stuff, to understand how cool evolution this binary stuff in the meaning of the safety rules. So you have this stroke of this spinner process. You need to handle server add, config the pack, and make the way that you want. So you start to figure out the algorithm of this and make that this spinner process persist, and make this tricky way to wrap and unwrap things to make safety rules like you want. But this subject going off of the scope, because you can kill these safety rules. It's a way to prove how this process could work under the hood. This binary process is an interesting way to see could we work in remote service. So let's replicate this spinal process to understand more things about. So of course you have the put stroke, this spinal process, of course have this T. You need to put some data, you need to handle chill version. We also serve address to the socket address. So we need to configure the path of this spinal process. It's this path that they make. So we also have this phantom data that's in the IoT. So far you have here the first stroke of this spinal process, that is understand how could we work in this mesh, this object going off of the scope, and understand what will happen if you kill these safety rules. Remember that the safety rules are making for the commit rules, for the bot rules, and how handle the ownership of the private keys in a security way to understand the BFT protocol. So let's see more things about this spinal process. You can find that it's a service for the consensus and prove the safety rules in different conditions and start to build this binary stuff to solve how it will work under the hood. So it's an interesting way to see this spinal process. Also, in other videos we saw that the safety rules are the consensus, update, start new POC, construct a SIM vote, SIM proposals, and of course the sign time off. So it's an interesting way to see these safety rules. Then we have the thread of this. We can replicate this thread service to understand the ways of this. So in this thread you have the chill, the bundle, then you can make a server, the socket there, because the maker that works like spinal process. So you have this data in this thread service. So this thread client is the actual owner of the thread, but is the context of the consensus and safety rules is on the client side of the operation, and it's make query requests to safety rules. So this thread service make the requests to safety rules and makes the queries and requests for the safety rules, but in the client side of the operation. You can find here all the data that you need to make this thread service to make a better performance and a way to see this remote in the remote way. So you can see that you are handled the socket idea to make a better performance of this, because you are using this kind of string that works in Amazon Web Service instance. So it's a way to handle all the data that are in the BFT protocol specification. So let's move to see more things interesting in the safety rules. So we can find here the last, it's the consensus state. Also in this last consensus state you can find all the data that these have, and you can find that is the POC, the latest POC round and preferred round, and then you need to return the preferred to the next block. Of course you need the counters. You have a vectors, interesting medical vector, and you have your own metric about this. let's see more about the remote service that is connected with the spawn and process and the treat service. This implementation. So let's figure out, trying to understand. So you have this remote service function. So you have a lot. You can see that this remote service is working in the side of the client. So to work in this way to understand how this is working. So let the network client specification, so server addresses. So let the service instance of this way. Let's remote client have this new. You need to handle the IPv4 addresses protocol specification. So you need to serialize the client and define new clients. You propose a service of this. And finally, function from server address. And you can handle this address. And then you have this executable this service, how this will be processed, and the serialize of the clients for the remote client. So it's a way to handle all the data that you have in this BFT protocol specification. So this you cannot find this in the paper about the state machine replication of the Libra BFT protocol, but there is things that the Rust language have for handled remote clients. So remember that remote client is connected with the spined process. This spined process, you can find here that's remote service. It's only for this process. So you in this remote service you have the spined process and the thread service. So you need to handle and manage all the client side of this data that start to connect in so many ways. So my time is over, so see you in the next video.